is an MPC day, and we're gonna start the morning. Peter's gonna start us off with kind of the basics, I guess, and we'll take it from there. Thank you.
Great. Thank you very much for the introduction, and good morning, everyone. And yeah, I guess I'll just say thank you to all the organizers for putting together this wonderful program. It's been a great week so far, and I'm looking forward to more of the summer. Okay, so today we have a few talks on secure computation. So I'm going to be starting with this lecture for the next hour, which is kind of a whistle-stop tour of the fundamentals and a lot of the basic concepts in secure computation, ranging from secret Turing-based protocols in the honest majority and dishonest majority setting through to correlated randomness and garbled circuits. And then after this talk, Alette will be jumping in remotely, and she'll be doing a more advanced session on function secret Turing, pseudorandom correlation generators, and other applications. And then I'll continue that this afternoon, looking at different ways of getting secure computation with sublinear communication complexity. And in particular, I'll be focusing on something called homomorphic secret Turing, which is a fairly recently developed set of techniques that can be used to do this. Okay, so let's get started. What is secure computation? So when I say secure computation, I guess I and most people usually mean secure multi-party computation, or MPC, where we have a set of parties here, 4 parties, each with some private inputs, and they want to jointly evaluate some function of their inputs, which of course normally you could do just by putting all of the inputs in one place, computing the function, and then sending back the outputs, as if you had a trusted third party here. But of course, this is cryptography. We don't trust people so much. We want to do this whilst preserving privacy of the inputs. So in MPC, the parties will usually do this by running some kind of interactive cryptographic protocol. Okay, so why would you care about MPC? Well, on the one hand, if you care about applications, maybe you're more on the practice side of things, then especially I'd say in the last 10 years, MPC has seen a huge array of blooming applications and startups and companies deploying all of these kinds of things for various use cases. It started out back in Denmark in 2009 with these famous sugar beet auctions. But since then, it's progressed into a huge array of different areas, including auctions and financial trading for private trading and markets, a lot of interest in private data analytics and machine learning using secure multi-party computation recently. And then there's a whole area called threshold cryptography, which is about kind of hardening security of secret keys, which is stored to protect databases or authentication mechanisms. And this often uses MPC to split up secret keys into different places while being able to do useful computations on them. And if you haven't seen it, there's this really great website I came across recently, actually run by people here at Berkeley, where you can see this list of deployments and companies which are actually using MPC and read a little bit about the different kinds of applications. Okay, but I know, on the other hand, this is also a theory workshop, so maybe you don't care so much about applications, but then I still think you should care about MPC. So it's, I guess at a more kind of philosophical level, you can kind of view MPC as kind of the most general form of cryptography, right? You want to compute any function, maybe allowing some interaction amongst the parties. You can kind of reframe any cryptographic task as MPC of some kind, if you like, and study it from that perspective. And looking more concretely, also, if you look at different areas of cryptography and computer science, there are very close connections between topics like zero-knowledge proofs, where on the one hand, we have things like MPC in the head, which can be used to build zero-knowledge proofs, and also zero-knowledge itself can be used to enhance security of MPC protocols, and other connections like error-correcting codes, communication complexity, and other advanced functionalities like functional encryption, obfuscation, often use tools that were first developed in the context of MPC. So chances are, if you're doing some kind of crypto, you're probably touching on aspects of MPC. Okay, and of course, this means that MPC has by now become a vast field. So there's a huge number of different settings you can consider when starting to study this topic. It's probably possible to pick just kind of 1 or 2 and then dedicate your whole life to this. So it can be kind of overwhelming when you first get started, and that's, I guess, kind of the purpose of what I want to do today is just to get through some of the very basic concepts and give a broad overview of what's possible. So just getting into some of these. So when we think about adversaries in MPC, of course, we can have passive or active adversaries, where active adversaries may deviate from the protocol, and passive ones are supposed to follow it. We have the corruption threshold, usually called T, out of n parties who may be corrupted by this adversary. This is usually divided into the two distinct cases of an honest majority of participants or dishonest majority in the protocol. And when you look at the function itself, it's maybe not even obvious how this function should be specified, right? Okay, as theoretical computer scientists, we all like circuits, but you can also think about Turing machines, RAM programs, other representations of the programs, which maybe will be more useful for different kind of computations you want to carry out. And then, of course, when you have an interactive protocol, you need some kind of network, and there's always going to be assumptions on what kind of network this is. Is it reliable? Does it have private channels? Do you have broadcast channels? And all of these kind of factors can, even just a small change here and there, can have a very big impact on what you can do in MPC. So with research in MPC, we usually ask the kind of basic feasibility questions of what's possible under what kind of assumptions and settings. And especially what's becoming very popular these days as MPC is becoming more practical is what kind of efficiency can we carry out these tasks. And this can be measured in different ways. I guess the main ones would be communication complexity, so the amount of data sent over the network, the round complexity, the number of rounds of interaction in a protocol, and just the computational complexity of each party in the protocol. Okay, so let's get started back to very basics and just go over a formal definition of what it means for a protocol to be secure. So you've seen in the zero-knowledge talks yesterday some idea of how security is defined for zero-knowledge proofs. And with MPC, this is somewhat similar to this simulation paradigm used to define zero-knowledge, but a little bit different because we have this more general kinds of protocol. So we use this real ideal paradigm where on the one hand we have a real protocol. Here this is two parties between Alice and Bob who are running some protocol with the inputs X and Y, and at the end of the day, the honest party, Bob here, will output something, and then the adversary will output something. But what we really care about when we're looking at what the adversary might learn is, okay, what has the adversary seen during this protocol? What are the messages it's seen, and what is its input? And this can all be captured by what we call the view of the corrupted party. Ideally, we want that this protocol doesn't reveal to the corrupted Alice anything more than she can compute, given the input and the output of the function evaluated on the two parties' inputs. And this is maybe not so intuitive a concept to define formally, like what does it mean to not learn something? And this is where this simulation-based paradigm comes in, where we say that, okay, if you give me some adversary who claims to be able to learn something about a protocol, and I say, okay, you give me that adversary, I will give you a simulator which will output exactly the same view as this adversary, given only access to the inputs and outputs of the function that the adversary would learn if talking to a trusted third party. Okay, so the simulator gets the adversary's input, the value X here of Alice, and then can send this to the trusted party and get the result of the function. And then we'll have to output some kind of view prime here. And of course, we want that these things will be indistinguishable. So note here that this indistinguishability is not just among the views of the corrupted party and the simulated view. We're also looking at the output distribution of the honest party. And firstly, this captures correctness, which of course we want. But secondly, in the case of randomized functionalities, it's actually important to look at these as a joint distribution and not just analyze correctness and security separately. Okay, so this is the basic definition of passive security. Active security is a little bit different, but follows along the same kind of simulation paradigm. And of course, we can have different kinds of security. It can be perfectly indistinguishable. These distributions are identical, or statistical if there's some maybe negligible difference between the distributions, or computational if we're relying on some hardness assumption and they're only computationally close. Okay, so perfect security is, of course, the best thing you could hope for, right, with this definition. So can we do that? No. And it turns out, okay, if we look at the case of two-party computation and consider maybe one of the most basic functionalities of just computing the AND of two input bits, this is sadly impossible information theoretically. I think there are many proofs of this result. I think the one I like the most is in this textbook by Kramer, Damgaard, and Nielsen on secure multi-party computation. I can recommend taking a look at that if you want to dive deeper. But for now, I'll just note that this quite easily generalizes to any number of parties, as long as at least n over 2 of the parties can be corrupted. And you can see this by kind of doing a kind of player emulation technique, where if I give you an n-party protocol, then I can turn this into a two-party protocol by having Alice and Bob each just emulate half of the players. Which means, okay, if the original party tolerated at least n over 2 corruptions, then the new protocol should tolerate at least 1 corruption. Okay, so this is impossible, and is pretty fundamental, so that doesn't seem good. So there's two ways we can consider relaxing this definition. Of course, we can go for statistical security, which turns out to still be impossible here, or even better, computational security. And we can alternatively go to the honest majority setting with more than 2 parties. Okay, so I'll start by giving a brief overview of honest majority MPC and the fundamental feasibility results there. So this line of work goes back to the 1980s when MPC began with the BGW and CCD protocols based on Shamir secret sharing. If you have a passive adversary, it turns out you can do perfectly secure MPC as long as no more than, so fewer than n over 2 parties are corrupted. And this is in a model where the parties have private communication channels over the network. It's kind of inevitable that you need at least some kind of private channels to do MPC. So you might think that, yeah, this is perfect security, but in practice, actually, you're probably still going to be relying on computational assumptions when you deploy this. But it's still nice to know what you can get. And when you jump to active security, it changes a little bit. So now, if you want perfect security, you have to have t less than n over 3. And instead, if you have t less than n over 2, there are protocols that still get you statistical security, so just with some tiny failure probability or cheating probability for an adversary. But this additionally requires a broadcast channel. And finally, in the dishonest majority setting.
So, sorry, the third line there, it's for which protocols? Like for which functionalities? Or I missed the.
This is for any functionality.
Oh, because you assume broadcast.
Yes, yes,
Okay.
exactly. You assume broadcast. Yeah, yeah. And then in the dishonest majority setting, where any number of parties or all but one of the parties might be corrupted, we know that we need computational assumptions. And in this case, if you have an oblivious transfer protocol, this turns out to be complete for MPC, and you can securely compute any function. With passive security, with active security, there is still a slight issue that we need to relax the definition to allow the adversary to abort the protocol, potentially after learning the output of the function, and leading to what we call a fairness issue, where the adversary might learn the results, while the honest parties don't learn anything. So this is kind of inevitable in the dishonest majority setting, unfortunately. So security with abort is kind of the standard definition here. Okay, so let's move on to looking at some protocols. And I'm going to start with secret sharing based MPC protocols, which kind of have the same structure, whether you're in the honest majority or dishonest majority setting. The idea is that we represent the function we want to compute as a circuit. It could be a Boolean circuit or an arithmetic circuit over some finite field. And then the protocol starts with an input phase where each party who holds one of the input wires will distribute a random secret sharing of this wire to the parties in the protocol. I'll say more about how you can actually do this secret sharing in a minute. But then after doing that, there's a computation phase where we kind of execute the circuit in a gate-by-gate manner on these secret shared values, which I'm denoting as values in brackets to note that no one knows this value, but they hold instead a piece of it. And then for each gate, we need some kind of protocol such that given shares of the inputs, we can get shares of the output. So that finally, when we get to the output wire, we have this special shared form of the output, and the parties can reconstruct this to learn the result. So this is a common structure in probably like the majority of MPC protocols you'll ever see, which is nice because there's not very many things you have to worry about when thinking about this. First one is, I guess when you look at the evaluation, we have different kinds of gates in the circuit, and most commonly, if we have addition and multiplication gates, then addition gates usually turn out to be kind of free by relying on a linear property of the secret sharing scheme, so that if parties locally add shares of the inputs, then they get a share of the output. This can typically be extended easily to affine gates, where you have multiplication with a constant, and addition of a public constant. I'll use this notation to denote that this secret shared value as this affine function applied, so that you get a secret shared result. And as usual, multiplication gates turn out to be more challenging, and this is where the techniques differ a little bit depending on this precise setting you're in. Okay, so let's jump to honest majority. Shamir secret sharing is the most fundamental tool used in honest majority protocols. I guess if you've covered any crypto course, you've probably seen this. This works over a finite field here, FP, and we have a secret S. And to distribute shares of this secret, I'm going to sample a random polynomial of degree T, where T is the corruption threshold, and compute n evaluations of the polynomial just at the points 1 up to n, and then fix the evaluation at 0 for the constant coefficient of the polynomial to be equal to the secret S. Okay, and as long as no more than T parties collude, then there is always kind of one degree of freedom missing to be able to uniquely determine this polynomial. This standard Lagrange interpolation says that we need T plus 1 evaluation to be able to reconstruct the polynomial. So this is a perfectly private secret sharing scheme. Once you have T plus 1 parties, of course, you can reconstruct the secret. You can even reconstruct the entire polynomial, which turns out to be useful to get some kind of error correction when you have active adversaries. And in general, the kind of basic requirement of this is that you're working over a finite field which has more than n evaluation points, so that you can compute n shares and still have 1 point left for the secret. This can also be extended to more general rings, even non-commutative rings, if they have a certain kind of special structure where with a large set such that pairwise differences of the set are invertible in the ring. Okay, so how do you multiply two shared values using Shamir? Well, the nice thing about Shamir is it actually kind of already has a multiplicative property. So if I take two sharings of values x and y, sampled using random degree t polynomials, then if I multiply two evaluations of these polynomials at the same point, then I just get a valuation of the product polynomial. And this is a degree up to 2t polynomial. So if all parties compute this product of their shares, then you end up with a new sharing, which has the product of the secrets in the original constant coefficient, but now it has degree 2 times t. So this is almost getting us to what we want, but we have this problem that, okay, now if we evaluate a circuit and do this at every multiplication gate, at some point this degree is going to blow up and we're not going to have enough points to be able to reconstruct the secret anymore and everything's lost. So we need to add to this some kind of degree reduction step. And the original BGW and CCD protocols do this by having each party take their share, Zi, of the new product polynomial, and then reshare this by creating a new set of shares and distributing them on the parties, and then performing Lagrange interpolation on these reshared values. So applying the linear interpolation formula to reconstruct the secret in a kind of already secret shared form. So this is a super elegant approach where just adding a little bit of interaction for each multiplication gate, you can now evaluate an entire circuit while keeping the degree t for each multiplication gate, just temporarily increasing to 2 times t. And this is where this n greater than 2t requirement comes with honest majority MPC. Okay, so in terms of efficiency, the big drawback of this is that every time you do this resharing step, you now have a quadratic communication requirement to distribute the shares. So there is another protocol called the Damgard-Nielsen protocol from 2007, which I'd say is probably the most popular protocol that's used in modern MPC today for honest majority, which gets this down to linear in n. And the idea is that it relies on some kind of setup phase in the protocol, which will generate random double sharings, which are Shamir secret sharings of a random value r shared at degree t as well as degree 2t. So if we're given some setup that distributes these to the parties, the down multiplication can be done very easily by doing the first step as before, where we locally multiply shares and get a degree 2t polynomial, and then take this degree 2t sharing and subtract from it the random sharing r at degree 2t and reconstruct this. And one kind of trick is here we'll reconstruct it to party P1, and then P1 will keep the result so that we can kind of do this with linear complexity instead of having everyone send shares to everybody else. And then P1 will compute this xy minus r term, send it back to everyone else, and then they can compute, they can add to this the original r term shared at degree t, and we'll get a degree t sharing of the value z.
So the point is by masking it with R, you don't lose security by giving it to one party.
Exactly. Yeah. Yeah. So this is perfectly secure, essentially like a one-time pattern. And if you look at the two steps which have interaction, then this can be done now with linear complexity and the number of parties instead of quadratic. The maybe slight downside compared to other protocols is that now we have 2 rounds of interaction where we send this to P1 and then send this back to everyone else. But I think this is usually a worthwhile trade-off in practice. And of course, one catch is that I haven't said how you do this pre-process. Sorry?
What about denial of service?
This is passive security. Yeah, everyone follows the protocol. Of course, at some point, we have to generate these random double sharings. We need one for every multiplication gate now. But also in the Damgard-Nielsen paper is a really nice trick to pre-process these in a batch using a nice randomness extraction technique to get an amortized linear communication complexity also for these. Okay, so yeah, as I said, this protocol is basically used in the state-of-the-art MPC protocols with some small optimizations and tweaks here and there. So there's this paper Atlas from 2021, which optimized this to reduce the total communication complexity of multiplication, including generating the double sharings to just 4 times n field elements. And additionally, if you want to rely on computational assumptions like a pseudo-random generator, you can reduce this to 2 times n. They also have some variants which have slightly higher communication and 1 round instead of 2 rounds. So there's many different trade-offs. Okay, what about active security? So if you look at what can go wrong in a passively secure protocol with an active adversary, then essentially all that can happen is when you do this, this opening of the multiplication to party P1 or any of the other parties, then okay, they can tamper with this when they send this back to the other parties. And this tampering is essentially equivalent to just adding some arbitrary error to the output of every multiplication gate in the circuit. This is a very weak form of active attack. It doesn't allow the adversary to really break privacy. It just breaks correctness of the circuit. And it also turns out to be something that is quite easy to detect against by adding some fairly lightweight consistency checks. And the state-of-the-art for doing this is a tool called fully linear interactive oracle proofs, which is a special kind of distributed zero-knowledge proof. We're trying to prove a statement on secret data that has been distributed among the parties. The nice thing is you can do this using essentially only a sequence of linear operations on the secret data over a number of rounds with public challenges used to get good soundness in this consistency check. Using these fully linear IOPs, to verify a batch of say, n multiplications, the communication complexity can actually scale only logarithmically with n. So for a large circuit, this is kind of almost for free in terms of communication, at least, to verify these multiplications.
So you don't use like verifiable secret sharing to go to active here?
Not in these protocols. So
So the verification doesn't go from the verifying secret sharing, it comes through the IOP.
yeah,
Verify.
so there is, you do have to, when you open things, you have to kind of still check that, you know, the points are on the correct polynomial to get consistency kind of at the output phase, especially there. But these protocols don't use VSS. So this basic approach, I guess the easiest way to do it only gets you security with a board. Because VSS gets you guaranteed output delivery.
I see, but security with the board for T over less than n over 3.
N over 2 with statistical security.
So wait, you're saying you have a protocol secure against less than n over 2 malicious parties, the statistical security, but we allow a board.
Yes, yes. But if you want guaranteed output delivery, so no abort, then there are also slightly more involved methods of using these fully linear IOPs, which can get you the same thing at a bit of a higher cost.
Like n over 3.
Yes, N over 3. I believe so. Yes, Tal?
Fully linear IOP is what? Is a protocol for how many parties? 2 or more? Is it information theoretic secure? Say something.
So it's an information theoretic kind of proof system, which you can model abstractly as just a two-party protocol between a prover and a verifier. And the idea is that the verifier makes queries to a proof string, kind of like an IOP or PCP, but these queries will always receive a linear function of the proof string.
So how is that fit with honest majority, multi-party?
Yes, so now that imagine the proof itself is distributed, secret shared across the parties. Each query is a randomly sampled challenge, and then you just compute the linear function across the secret shared data for each round of the proof.
Thanks.
Yeah.
So the communicational overhead is minimal, but the computational overhead is proportional to whatever circuit was.
Yeah. So you have to pay extra computation proportional to the circuit, at least for security with a board. I think it's a constant factor higher.
NC, the computational cost, or C?
Each party is paying the cost, so it's NC.
So the reason you need this fully linear is because you can do linear operations on the secret sharing.
Exactly. Yeah. And if you look at some of the concrete performance numbers from this Atlas paper, then if you want to do, say, integer multiplications over a 61-bit finite field, then you could do around 2 million multiplications per second with 3 parties and active security with a board, which is pretty good.
This was with broadcast or without broadcast? This product is for N over 2.
So for a board, you don't need broadcast. For GOD, you need broadcast. Okay, so now let's move to the dishonest majority setting. Okay, I said before, dishonest majority MPC requires computational assumptions. It's impossible to do AND without them. Now I'm going to cheat a little bit and say, okay, let's do some dishonest majority MPC, but without any computational assumptions. And how do we do this? We use what's called the preprocessing model, which I guess I also kind of mentioned when talking about these random double sharings, but a little more formally, imagine an ideal functionality for preprocessing which samples some correlated randomness. So random variables R1 up to Rn, and then distributes each of these privately to one of the parties. And then during the MPC protocol, when the parties learn the inputs, they'll use the randomness to help evaluate the function. So I guess the nice thing about this model is it's kind of flexible. You can do the preprocessing in advance if you want, potentially offloading some of the heavy work to produce this preprocessing ahead of time. And then the online phase can then be very simple. It can now be information theoretically secure, very lightweight, and cheap in terms of computational overhead. And in fact, you can even get just a constant factor slowdown in terms of computation per party compared with evaluating the plaintext circuit in the clear. So in this talk, I'm not going to say anything about where this preprocessing comes from. Alette should say a bit about that in her next talk. You can imagine it coming from a trusted dealer, which could be potentially a non-colluding third party who's part of the protocol. It could be some trusted hardware device, or maybe it's generated using an interactive protocol using cryptographic and computational assumptions. Okay, so I'm going to cover two main protocols in the dishonest majority setting. The first of these is called one-time truth tables, which I would say is probably the simplest general purpose MPC protocol that you can see. If you ever have to teach MPC to undergrads in about 20 minutes, then I definitely recommend this one. And also turns out to be kind of interesting for a number of reasons and actually quite useful. So I'll present the passively secure protocol, but this can actually be extended to multiple parties beyond 2 parties, and even with active security, with perfect security, when only one of the parties gets the output, which is, again, kind of the best you can hope for in this setting.
When you say inefficient, what do you mean?
You'll see in a minute. Okay, so we want to evaluate a function. And now let's look at the truth table of this function. This is the inefficient part. So if the function has n bits from each party, or 2n bits of input, then this truth table is of size 2 to the 2n. Okay, but we can represent this as a matrix here, just the toy 4x4 case. And now we're going to take this truth table and just randomly permute it by picking a random shift to permute the rows, and then pick another random shift to permute the columns. And this is all being done in our preprocessing phase, so ideal functionality, which is doing this secret shuffling of the truth table. And it's then going to distribute this among the parties in the following way. So we pick a random matrix as big as the truth table for one party, which is going to be a secret share of the permuted truth table, and then pick the other share, MB, by XORing the first share with this permuted truth table. So these are now just simple XOR sharings of the truth table. So we give each party one of the matrices, and then we also give one of the random shifts to Alice and Bob. Okay, so now how do we do the protocol? So Alice has an input X, and Bob has an input Y. Alice is first going to send her permuted input, permuted by this random shift R, by adding this modulo the number of rows. And then Bob is going to send his permuted input by adding this modulo S, so adding S modulo 2 to the n. And then if you look at the entry UV of this truth table, then you will get exactly the function evaluation at the input X and Y. So together with the value B, Bob will just extract that corresponding share from his table, send this to Alice, and Alice will XOR this with her corresponding entry of the table. So this is a very simple way of evaluating any lookup table using preprocessing. If you look at the communication complexity of this protocol, this is essentially optimal, right? Alice and Bob just send n bits each, plus 1 bit for the output. Communication is even independent of the function. This is a dream.
Assuming you don't count the preprocessing.
Yes. Assuming you don't count the preprocessing.
Not very dreamlike.
Yes, indeed. It's not. Yeah, plus we have correctness and privacy. But then we have this exponential storage cost of the preprocessing. And because, you maybe even have to generate this preprocessing in some way using some interactive protocol, this is going to be expensive. But I think this protocol is still interesting. It turns out to be actually useful in practical applications if you use it as a small building block as part of larger protocols. We'll see a little more about some ways this can lead to kind of interesting theoretical results in the afternoon talk. Okay, so how do we get something actually efficient? Well, here we go back to our secret sharing paradigm, where we'll look at MPC for Boolean or arithmetic circuits, now using the GMW protocol. So GMW uses additive secret sharing instead of Shamir. This is even simpler than Shamir, so secret X is just split into n shares. It's summed to the secret X, with the shares sampled at random. And we can do linear operations on shares in the same way by just adding the shares. We can add constants to get arbitrary affine gates. So once again, the only challenge is multiplication gates. And when we have this preprocessing model, the standard trick for doing multiplications is often called Beaver's trick, or using Beaver multiplication triples, where preprocessing functionality will give out random sharings of random values A and B, and a random sharing of the product A times B. And to use this, again, I look at X times Y and then do this trick where you're going to add 0 to both X and Y in different ways and expand these brackets. This is what you get. Just trust me for now. And if I separate out, okay, the red terms here are the preprocessed and secret shared random triple, AB and A times B. And look at everything else we have after expanding this. We have X plus A and Y plus B, and again, X plus A and Y plus B. So if we open these X plus A and Y plus B values, then now this whole equation is a linear function in these preprocessed secret values, so we can compute it without interaction. So this gives us sharings of X times Y just by doing these two openings of X plus A and Y plus B, which can be done in parallel in one round of interaction. And doing this opening, at least naively, will cost O of n communication across all of the parties.
Okay, so sorry, it's one round to get a multiplication.
Yeah.
But then, you know, you may need to do like.
Yeah, this is just one gate.
Oh, one
Yeah.
gate. Not.
Yeah. So if you look at the whole circuit, then now if we have a circuit with S gates and the depth of the circuit is D, then the round complexity will now scale with the depth of the circuit because we can, of course, parallelize all gates which are in the same layer. Preprocessing size will scale with the number of multiplication gates. Communication will scale with the number of multiplication gates times the number of parties. And the computation for each party is just proportional to that of evaluating the circuit in the clear times a small constant factor. So that's really nice, right? Okay, there's this communication that is proportional to the circuit size, but if you have a fast network and maybe you don't care about communication, then just being able to do MPC with a constant slowdown in computation, that's great. Okay, but this is passive security. Okay, let's think about what it takes to get active security. So now when you're using additive secret sharing, basically anything can go wrong with an active adversary, because you can just tamper your share trivially when you open a value, and there's no way to even detect that something went wrong. So there's a few ways we can deal with this. The kind of classic textbook solution from the GMW paper back in the 80s is to use zero-knowledge proofs, where you follow this commit and prove paradigm of committing to all of your randomness and inputs at the beginning, and then at each step of the protocol, running a zero-knowledge proof to prove that you executed the correct steps of the protocol using the committed randomness at the beginning. This is incredibly expensive. It's non-black box in the protocol and the cryptographic primitives that are used. This isn't so nice. So what I'm going to talk about today is I think, very simple and clean model of getting active security, which again relies on this preprocessing model using information theoretic MACs or message authentication codes to prevent parties from tampering with shares. Okay, so now instead of additive secret sharing, we'll augment this with some authentication mechanism. As well as the shares, X1, X2, and X3 here, the parties have shares of some MAC on the secret X. Well, these MACs are going to be additive shares of X times by some secret MAC key alpha, where alpha itself is additively shared among the parties, And I'm going to choose alpha to be the same for every single authenticated and shared value in the protocol. So if I have some authenticated secret shares of X, and then I have some authenticated sharing of Y, then we can still do the same as before. This whole thing is linear. We can add the sharings of X and Y. We can add the max of X and Y, and we still get a valid authenticated sharing of the sum. So these kind of max were introduced in the speeds protocol, or SPDZ, from 2012 and 2013. And the only thing we have to now take care of when we're using these in the protocol is, okay, how do we open things and actually check the max when we're using these in a protocol?
But what about multiplication? Don't we get alpha squared? For multiplication, don't we get like a square that we get?
So we just do linear operations for now,
Oh,
right? Because when we did multiplication with the triple,
always.
we only, everything becomes linear. Okay, so if we can open, we can do the whole computation. Okay, plus, I guess, a little bit of work to distribute sharings of the inputs, but I'm going to ignore that for now. Okay, and one of the ways you can open and verify these max is quite simple. So so imagine you first just send your shares xi and reconstruct the secret x, which now, if someone was corrupt, may have some error delta. And then we want to check that the MAC on X is valid without revealing this secret MAC key alpha, because of course that would compromise integrity for future openings of the protocol. The idea is to do this commit and open protocol, where each party computes this value with their MAC share alpha I times by the open value X prime minus the MAC share gamma I. And
Sorry, I'm confused. Sorry. What do you mean? What is X prime?
so X prime is what you, okay, so X is the actual original secret, and then if someone cheats, they might lie about their share when opening,
oh,
so you get X prime.
I see. So the delta is like a cheating.
Yes, delta is an error induced by the adversary.
Got
Yeah, so, okay, so if delta was 0, and then we sum up these DI values, then we should get something that sums to 0, right? Because this is sum of shares of alpha and shares of alpha times X. We should get 0.
This doesn't identify who actually cheated, shows us some.
No, this doesn't identify who cheated. That's more tricky. Yeah. Yeah, but once we have an error delta, then these things will sum to get delta multiplied by the secret MAC key alpha. Means if an adversary wants to be able to come up with such a DI which passes this check, then it needs to guess this value alpha times delta. So as long as we're working over a finite field, and alpha is sufficiently high entropy, so we're in a large field, then it should be impossible to pass this check without having learned alpha. Okay. And yeah, this is now specific to fields again, but I'll note that, like some of the techniques for Shamir sharing, this can also be extended to rings by slightly tweaking how things are defined and sampled.
Since the moment something is non-zero, you just abort, right?
Yes, yes. As soon as it's non-zero, you have to abort. In fact, yeah, you have to be a little careful in this, because once something is non-zero, the adversary has potentially also actually learned this MAC key, right? So you really don't want to do anything else with that anywhere else in the protocol. Okay, so that's the speech protocol, at least the online phase. So we can compare and contrast this with GMW, or the passively secure variant of GMW. Okay, look at what's the overhead of active security here. So first off, we work in a sufficiently large finite field. If we want to do that in the first place, then it pretty much comes for free, right? Because the size of these max is just one extra field element per secret sharing in the circuit, and the computation is just maybe a factor 2 or so more. So preprocessing, communication, and computation are roughly the same. Of course, if we want to do something like Boolean circuits, then we run into problems, because you can't have a random MAC key over a finite field of size 2, and you have to work in a large extension field, and then you get this security parameter overhead for the storage of the preprocessing.
When you say GMW with GMW, you mean with
with beaver triples. Yes, yes. It's not quite the original GMW presentation.
The processing is similar. Also, in the other case, you need similar type of preprocessing, correct?
Yeah, in both cases, it's multiplication triples.
Yeah.
With speeds, they're authenticated, and here they're just added to the set.
And that's why you need a little bit more, the lambda.
Yeah, so that's why, yeah, especially if the field is small, then you still need the max to be large. So they're typically in a large extension field, which gives you this security parameter overhead. But the communication costs, you don't actually have to pay anything in the security parameter, because you can still just, open things by sending small things over the base fields, and then do some kind of batch verification for checking max.
So you can think of speeds as a different way to turn GMW from passive to active, more
Yes.
than a totally different.
Exactly, yeah,
With people.
with preprocessing.
With preprocessing, just like GMW was not using preprocessing.
Yeah, it depends. Yeah, I guess basically it's using OT, which you can see as preprocessing if you like. Yep.
Which of these parameters is most important in practice? In particular, for example, communication versus round, or and in general?
It depends on your network, right? So I would say maybe it's more realistic in practical settings that you're gonna have parties who are perhaps further away and they have some latency between them. And then the rounds is gonna be the dominating factor. But I know some people, companies looking into deploying MPC where they have 3 servers located in that's maybe even the same data center, or at least different data centers in the same country. They have a fast connection between them. Then it might be the communication, it might be the computation.
But if they're very close, then it's harder to argue that they don't.
Yes, exactly. Yeah, that's why I say usually high latency, perhaps more realistic.
So the bottleneck is not clear.
It depends. Yeah, there's a lot of variables and a lot of different ways you can imagine deploying it.
There is something interesting, or maybe not interesting, right? Initially, kind of said that beaver triples is just kind of offload expensive stuff to preprocessing, but here it seems like to buy you something more, right? It seems like you don't need to get rid of this alpha square for authentication, right? Because if you do it naively, like multiplication would be non-trivial, right? So is there something different going on here? I'm trying to see. Was it beaver triple something?
I think it's just because you're authenticating the beaver triples as well, right?
Because but some point preprocessing, you're saying is beaver triples are independent, so you kind of do the same computation with authentications, and some we don't have to pay for authentication.
Yeah, beaver triples let you do multiplication at the price of addition.
Well, you do multiplication at the beginning. So
Yeah.
Yeah, I think all you're doing is just beaver triples, but now with this authenticated secret sharing scheme.
But in the pre-processing, you need to also authenticate the beaver triples, right?
Yeah, you have to work harder in the pre-processing.
So I think that's
So it's
maybe
kind
the
of
system.
similar, yes.
Yeah.
Okay, so that's all I'm saying about GMW and speeds. Now, I think for the last 10 minutes, I'll try and cover a little bit on garbled circuits, just to give a rough overview of that.
Two questions. So there are recent proposals like hardware C, PC, which shave off the extra n factor. How do they compare in real implementation?
Which results are you referring to, and are they all n-1 out of n corruptions? Or-
No, I guess they have.
Yeah, I think if maybe you can get dishonest majority with like a constant fraction of corruptions without the O of n factor using PEG secret sharing.
They are not like are they implemented in these libraries?
I'm not sure. Okay, so yeah, as we were saying, if the parties are located far apart, then latency can be a problem, and the round complexity might be the dominating factor in the cost of these protocols. So this motivates trying to find something better and overcome this O of D limitation in the round complexity. Okay, I guess, yeah, quickly, one of the tools we're going to be using here is oblivious transfer. which is an ideal two-party functionality with a sender who has two messages, x0 and x1, wants to transmit one of these to the receiver who has a choice bit b, and we'll learn just xb and nothing about the other bit. This is a two-party functionality. It's a special case of two-party computation. This is kind of the core building block of many MPC protocols that people have put a lot of work into trying to build, and there's many different OT protocols, but they basically all use some form of public key encryption type assumption. So it kind of lives on the level of public key encryption. But we're going to look at garbling circuits. So garbling actually goes back to Yao in 1986 or so, which even predates GMW, interestingly. So now I've kind of presented this in a slightly backwards order. But a garbled circuit is essentially a way of encrypting a circuit in such a way that you can only learn the result of the circuit on some input and nothing more about the intermediate values, or even potentially even the gates in the circuit. So we have a Boolean circuit here. Garbling is usually presented for Boolean circuits. And for any gate in the circuit, say an AND gate here, you can look at this truth table of the gate as a table of ones and zeros. And to garble this circuit, instead of thinking of ones and zeros during the circuit, we will think of random labels assigned to each wire of the circuit, where each label is now some cryptographic key. And we pick these for the input wires, the intermediate wires, and the output wire of the circuit. And then for each gate in the circuit, we're going to use these labels to generate a garbled version of this gate by encrypting the truth table of every single gate in the circuit. So now replacing the truth table with the corresponding labels for the input wires and the output wires, the idea is that we're going to encrypt the output wire of the gate such that if you're given the two input wires corresponding to the correct 0, 1 values, then you can recover exactly the correct output wire label corresponding to the correct output bit. And this can be done in a few different ways. So here I'm just using a hash function where I take the two input wire labels, hash them, and then XOR this with the correct output wire label corresponding to the truth value of the gate. Okay, so if you model the hash function as, say, a pseudo-random function or even a random oracle, then this should be a computationally secure, at least in some sense, deterministic encryption of the output wire labels K0 or K1. And when we generate these garbled gates, we want to shuffle the order of the ciphertext and then put these things together into a garbled circuit, which consists of these encrypted truth tables of all of the gates. Okay, so garbled circuits can be evaluated where if I start with the input labels corresponding to the actual inputs, so if the first bit is input 1, I get the first label. The second bit is input 0, I get the first label. And then I can use these encrypted truth tables to learn the output label for the next gate. For example, what's going on here? Yes. Yes, so when I get to this gate in the circuit, if I have, say, the input labels L1 and R1, then I can decrypt these by looking at the last row of this encrypted table, and we'll recover K1. Of course, there's a problem here that if I'm garbling and I don't actually know, what these labels represent, then I don't even know which row to look at in this encrypted truth table. So I need some extra mechanism to detect invalid encryption. And one way of doing this is to add some zero padding to the labels such that I can kind of trial decryption for every row in the table until I get one which has this matching padding of zeros. And then when I get to the output, I will get one of the two output labels, Z0 or Z1. And if in addition to the garbled circuit, I'm given, say, both of the labels for the output and I'm told which one they refer to, then I can look up in this table and recover the actual truth value and the result of the circuit. So this gives a way of evaluating a circuit where I'm only given kind of special information corresponding to the inputs of the circuit, and I can evaluate it and learn the results and nothing more. More formally, garbled circuits can be defined using a sequence of algorithms. So garbling algorithm which takes as input the function and some randomness and outputs a garbled function together with some encoding and decoding information, which is essentially the set of labels for the input and output wires. And then an encoding function, which maps the labels to labels corresponding to a specific set of inputs for the input to the circuit. And finally, an evaluation function, which takes as input the garbled circuit, the encoding inputs, and then outputs this final output label for the output wire, which can then be decoded using the decoding information. So this is a kind of nice abstraction and formalism by Larry, Huang, and Rodaway, which puts garbled circuits, which we've known for a long time, on a kind of nice solid foundations. And now garbling schemes in this syntax are used in a lot of cryptographic applications, not just secure computation, also other things like attribute-based encryption, functional encryption, and more. Okay, so when it comes to garbled circuits, actually first, so let me go very quickly through how we use these for two-party computation. So we have one party who's going to garble the circuit. This is Bob, who's the garbler. And then Alice is going to evaluate the circuit. And the first step is for Alice to learn the labels corresponding to her input, which is where oblivious transfer comes in. And then Bob will send over the garbled circuit together with his garbled input labels, which allows Alice to evaluate this and obtain the garbled output, and then decode the result of the function using the decoding information. So if the OT protocol runs in 2 messages, then this whole protocol can run in just 2 messages, with one message from Alice to Bob, followed by another message from Bob to Alice. So we get what's essentially the best possible round complexity for two-party computation. So this is really nice, much better than something that scales with the depth of the circuit, like in GMW. Now, the main thing that we're paying here, compared with GMW style protocols, is that you have to send this garbled circuit, which might be pretty large. So each gate in the circuit now contains a number of ciphertexts. So these are going to be order of security parameter in size. So a lot of the research efforts in garbling are looking at reducing the size of garbled gates. Was trying to keep this nice efficiency of just being able to use hash functions or pseudo-random functions to derive these encryptions and decryptions of gates.
So the size of the circuit is proportional to the size of the circuit, but also in GMW you have to do one communication per.
Yes, yes.
So the total communication seems common.
Yeah, so now it's the size of the circuit, but it's size of the circuit times by the security parameter. Even for a Boolean circuit, which for GMW you don't have to pay, depending on the preprocessor.
Why did you present GMW with a pre-processing and you're presenting Yao without, like, why don't you present them in the same?
Well, Yao isn't really amenable to preprocessing in the same way. Okay, you guess you can potentially preprocess the garbled circuit, and then you don't have to send that, but that's like a much stronger model of preprocessing. It's circuit dependent. It doesn't quite seem as fair.
Okay, so why did you allow yourself to do pre-processing for GMW?
I think preprocessing is a clean and simple model, and then Let will also talk about how to instantiate the preprocessing. So, yeah, the pieces will get filled in, hopefully. Yeah, so for Yao garbled circuits, I guess no one really has in mind exactly what Yao's approach was because he never wrote it down. At least the textbook approach that I wrote up has a multiplicative factor of 8 times the security parameter for every gate in your circuit. There are some nice optimizations like point and permute, which can get this down to 4 lambda, so you don't need to have these this zero padding in the ciphertext. And then other optimizations like row reduction, and another paper from 2015, which can get down to the best known result of lambda bits to garble an XOR gate and 2 lambda bits to garble an AND gate using only a pseudo-random function. If you allow stronger assumptions, what's called a circular correlation robust hash, which is basically a special kind of hash function that can be shown as easily realized by a random oracle or an ideal cipher. Then you have this free XOR trick, which allows you to garble XOR gates completely for free, at least in terms of communication. So you don't have to send anything for XOR gates in the circuit. Now this is nice because it also matches what you get for GMW, where you don't have to pay for XOR gates in a Boolean circuit. And then the state of the art for AND gates is this 3 halves paper by Roy and Rosalek from 2021, where the size of the AND gate is 1.5 lambda bits. And there's a very recent result by Lance and Mike and another co-author, Jake, I believe, which has some model of lower bounds for these garbling schemes, which essentially shows that, okay, under some assumptions, these schemes are basically optimal. So, yep.
Like in what model?
In what model? I don't know. Maybe it's better to take this to the break with Lance. Yeah. Yeah. So maybe that says that this line of work is now solved, and there's nothing more we should do there. Maybe if you look closely at the model and talk to Lance, you might find out, what you need to explore and how you could bypass this. But I'm not sure. So, of course, all of these works are looking at just garbling a single gate, like XOR or AND gate, one at a time. So kind of orthogonal to this has been another line of work looking at higher level optimizations to the whole circuit, where you can actually do much, much better for certain types of circuits. One example is circuits with conditional statements. So where I have, say, n different circuits, and then I want to obliviously select which one to evaluate based on some secret value, maybe some intermediate value in the computation. And you can garble conditional circuits with communication proportional to roughly the cost of garbling one of the branches using these stacked garbling techniques by Heath and Kolesnikov, which basically gives you a garbled circuit where the size is proportional to the longest execution path of the program. And that's really nice. These techniques and other techniques for things like garbled lookup tables have recently used also to build garbled RAM, with actually now pretty good practical concrete efficiency. So garbled RAM was first studied more than 10 years ago with very theoretical constructions based on one-way functions. But now it's actually pretty efficient, and at least for reasonably large memory sizes, you can get kind of close to the best possible, or well, what looks like it might be best possible cost of just logarithmic overhead per memory access with this multiplicative factor in the security parameter. This is all just using mini-crypt style assumptions, pseudo-random functions, or maybe the free XOR assumption. And then another line of work, which I will maybe talk a little bit more about this afternoon, is, okay, how can we beat this lambda bits overhead per garbled gate? Okay, so for certain kinds of circuits, we have specialized tricks which can work for maybe RAM or branching in the circuits, but for an arbitrary circuit, we still don't really know much better, at least in minicrypt. So even if you allow really heavy hammer, like fully homomorphic encryption, it's not even clear how to build a garbled circuit, with good asymptotic complexity, maybe independent of the circuit size with FHE. There are these really nice works by a number of authors who I think I haven't quite got right on the slide, but some of them are in this room, which get reusable garbling and other cool applications from learning with errors using, I believe, FHE together with some more advanced attribute-based encryption type techniques. So you can get reusable and somewhat succinct garbled circuits where the size only scales with the depth of the circuit. So you might ask, okay, what can you do without relying on LWE, without relying on this kind of heavy hammer of fully homomorphic encryption? And there are some very recent results looking at doing garbling under algebraic style assumptions like DDH or decisional composite residuosity used in Allier encryption, which can get you, I guess, the best general result is a log-log factor saving in the circuit size. So you can garble a general, at least layered circuit with some mild assumption on the structure of the circuit, where the number of bits in the garbled circuit is proportional to C divided by log the circuit size C. No lambda. Yeah, so log saving looks like it's pretty small, but when you combine it with the lambda saving, this is actually, even concretely, maybe quite a significant improvement.
The lambda, where did the lambda saving come from?
I guess it's just in this work.
Oh, it's not
Yeah.
You're saying for LW, you can get a log, and for this, you can basically get a little bit more than lambda. Independent.
Yeah, I mean, so LWE, okay, you have poly and lambda, but now just in circuit depth, which is a big saving, right? Here, okay, what I've missed out is there's an additive term of poly and lambda, which of course is inevitable.
If I don't care about this log, sorry, just the title of the thing sounds like a big deal is to save order of lambda.
Yes, if you don't care about the log, then now it's C plus poly and lambda instead of C times lambda.
But still, but it's very recent work. It's not like something.
It's very recent, yeah. Yeah, there's I think these are the first papers to get this without relying on LWE.
So comparing this to GMW, so you are gaining number of rounds, paying in the basic version in total communication by a factor lambda. Here you are trying to reduce the communication. And so in the LW setting, you are actually gaining a lot in communication over GMW, correct?
Yes.
But on the other hand, these are all passive security. There is no active.
So at least in a theoretical sense, any of these protocols can be translated into active security whilst preserving the communication complexity using the right kind of zero knowledge proof. So yeah, but yeah, these are all only looking at passive security, I think.
The work with path secret sharing, does it help here? I mean, like path secret sharing, does it help?
So this is all two parties. So packet secret sharing is usually just for the multi-party side.
Okay, let's take the questions after we're late at the break.
Yeah. Cool.
Oh,
Thank
that's
you.
it.
That's it. Yeah. Yeah.
So let's take a 20-minute break and then I make the snacks. Oh, guys, 1 second, I'm supposed to